something. When the plus is positive, what is it related to? And so that's probably the best argument for lambda plus being 0. Yeah, so I guess something should be 0 unless there's a good reason for it not to be 0. That's a conjecture.
Maybe as usual, we can push it a little more back. Space, right?
If I give it here, people can't see. Can't see the.
Maybe push it a little bit more, a little further. Yeah, yeah. That's
Maybe you can tell it so that it's.
All right, so happy to start the second talk of the morning. And speaker is Shanta Laishram, the classical aesthetic.
Yeah, thank you very much. And so first of all, I want to thank the organizers, particularly Kalyan, Azizul, Prem, and plus others for this kind invitation and for organizing this really wonderful conference. And happy to be back to Kerala after a long time. So today I'm going to talk about this stability of higher degree polynomials. So this is also a bit related to the Prof one. This is a joint work with Ritumani Sharma and Himanshu Sharma who are at IIT.
Let's click once.
So as you have seen it before too, so a dynamical system consists of a set and functions from the set to itself. So basically, we define this function from set to set so that this it can permit iteration. And for n bigger than or equal to 1, so the nth iterate means you iterate the function n times. So, and by convention, when n, like you put phi of 0 to be the identity map. And the forward orbit is the, like, if you start with an element alpha in the set S, then forward orbit means the phi alpha, phi square alpha, phi cube alpha, and so on. So you also aware of this periodic point, so let me just define once again. So given the alpha in S, we call it periodic if for some n, so n iterate is same as this alpha. And periodic means after some states it becomes periodic in the sense that phi of so there exists n m bigger than n such that phi of n alpha is same as phi of m alpha. So and if a element is not periodic, then it's called a one-rank point. So for example, so I just want to give you an example here. You take the set S to be the finite field of the elements. Then the map given by G power, okay, so there's a type here, P of X to be X power P. So the periodic points are the whole of FP, whereas if you take the map to be X power P minus 1, the periodic points are just 0 and 1. So actually the points can quite vary. So it's actually our problem to find polynomials of some fixed degree. Yeah, so if you fix the degree D, then for which primes there's a polynomial of degree that that degree such that all of FP are periodic points is still hard problem. So anyway, I won't go into it today. So I'm going to talk about this stability of polynomials. So let me formally define what is this. So you start with a field K, and you take a polynomial of degree D, which is at least 2. Then we call F stable if degree iterate is irreducible over K. So F is irreducible, F2 is irreducible, F3 is irreducible, and so on. So of course, the first thing what you want to ask is that if you start with an irreducible polynomial, whether it remains stable. So answer is no, as you can see from this example. So if you take the polynomial x square minus x minus 1, you see that fx is of course irreducible over q. Then if you take f2 also, actually is irreducible, but at f3 it remains it's not irreducible anymore. We have a factorization x power 4 minus 3x cubed plus 4x minus 1 times the other factor. And another example is x square minus 4 by 3. So this is also of course irreducible, but then in fact at the second time, I mean like f2 second iteration itself is no more irreducible. So so now I will say something about this eventually stable polynomials. So of course, what stable means the only is irreducible, all the threads are irreducible. But then, as you can see from examples that is not only irreducible polynomial, it's interest. The interest where is no more irreducible. Then we want to also look at another kind of polynomials where, okay, it need not be irreducible, but you can like bound the number of irreducible factors. So if so you start with a polynomial f and we call it eventually stable if the number of irreducible factors of that of the f for any n is bounded by a constant which depends only on f. It doesn't depend on n. So over, I mean you vary n, but the number of irreducible factors it remains constant. So this is actually a property of iterated pre-images of 0. So now actually I'm going to generalize it over rational function. So you start with the field k and take a rational function p. Now you so rational function you write it as f by g. So for every n, the nth iterate you write it as fn by gn, where fn and gn are co-prime. And for a alpha in positive space over k, we said that phi alpha is stable over k if fn g minus alpha gn g is irreducible over k. So basically, I mean, if you take f phi to be the polynomial, that's exactly the definition I stated before. So otherwise, for a rational function, this is how we define. So for every n, fn minus alpha gn is irreducible over k. So in fact, the stability condition is quite strong. So for a field k, it can be stable, but if you take a finite extension, it need not remain stable. So we want to look at this weaker condition called eventually stable, where stability where I mean if this eventually stable over a finite field, then over any extension it still remains eventually stable. So so the phi to be the rational function. Now phi alpha is eventually stable if number of irreducible factors of f and g minus alpha g and g. So this is bounded by constant which depends on the original this rational function phi and alpha, and not on n etc. So basically, remember that phi n of alpha is actually fn by gn. So like so if you take the point at infinity, then we I mean like so this is for alpha, not the point of infinity. If you take alpha to a point of infinity, then we call it eventually stable if number of irreducible factors of gn is bounded by constant which depends only on alpha and phi. So basically, this eventually stable is equivalent to the fact that so as I've told before, so it has a nice property says that if it's eventually stable over a field alpha L, then it remains eventually stable over any finite extension. Yeah, no, so actually that's the over case eventually stable means only finite extension still remains the same. And this is also equivalent to the fact that for some n, there is some n for which phi and alpha is eventually stable. And another equivalent condition is the fact that if you have for every sequence beta 1, beta 2, beta 3, etc., we satisfy phi of beta 1 is alpha and phi of beta n is beta n minus 1 for n bigger than or equal to 2. So the degree of this extension k beta n over k beta n minus 1 remains d for all substantially large cell. So here d is the degree of phi. So that's the maximum of the degrees of f over g. Phi is f by c. Okay, so now let's look at one example. Let's start with the field Q and look at polynomial x square minus 1. This was actually also this in chapter 1 also it came up. So basically what you can see is that if you look at the second iterate, that is x square minus 1 whole square minus 1, that is divisible by x. So f2x is no more because irreducible. But what we can say more. Actually, f of n divides f of n plus 2 for every n bigger than or equal to 1. So x divides f2 of x, which divides f4 of x, and so on. So here we cannot control the number of irreducible factors of fn. So this for this f, so fx equal to x squared minus 1 is not eventually stable. So Jones and Levin 2017 they proved that if you start with a rational function over k and a periodic alpha, then this phi alpha is not eventually stable over k. So based on their work, so the following conjecture was made. So if you so if alpha is a periodic, of course, then this phi alpha is not eventually stable. What can you say about phi alpha when alpha is not periodic? So basically, it was conjectured that this is eventually stable. So now let's recall the conjecture. The conjecture says that if you start with this phi rational function for which alpha is not periodic, then phi alpha is eventually stable. That means every iterate, if you write Vn as Fn by Gn, then Fn minus alpha Gn is has finitely many irreducible factors. So here I want to tell you that every rational polynomials of degree 1, like the linear polynomials of, so they are all stable because if you keep any number of iterations is still going to be stable. And so when we consider the eventual stability of phi, so we have to consider loss with degree at least 2. And it's a kind of fun exercise that if you start with a polynomial which is Eisenstein, then every iterate of f is Eisenstein, and hence f actually remains stable. So now I want to go to this. Okay, so there is the general definition of stability. So I want to go to Q. So I'm going to concentrate over rationals. So refresh what is stability that means. So you start with a polynomial over rationals. So stable means simply iterate is irreducible, and eventually stable means there is a finite number of so number of irreducible factors is bounded by constant. So we are interested in the stability and eventually stability of this G power D plus B, where D is L is 2 and B is a rational number. So I'm going to consider this particular the families of these polynomials. So what do we know about it? So you write G power, so D is L is 2. So just one more time. Yeah, so I always like G and X, there's always some sometimes use X, sometimes J. So that's so G power D plus B, you write it as G power D plus A over C, or B is A by C, and A is not equal to 0. So it was proved in 2015 in an IMR paper by Hamlet, Jones, and Malu that if you have this, if you take A by C where A is not equal to 1, then this FZ remains eventually stable. First, I mean, if you just take polynomials of this form G power D plus 1 over C, it's not completely not completely known. It's not even for D equal to 2. That is for quadratic polynomials of form G square plus 1 over C. So we're going to instead of D power D plus A by C, we're just going to consider polynomials of form G power D plus 1 over C. So this is the theorem actually we had. So D start with a positive integer D and a polynomial G power D plus 1 over C, where C is not C is an integer. So what we are not able to actually prove that for is stable for every C, but what we can prove is the following. So if you take D equal to 2, that is G square plus 1 over C. When C is congruent to 1 mod 4, then all the iterates are irreducible. So there is G power D over 1 over C with C congruent to 1 mod 4. It's this is given. So I'm going to tell you what happens if C is not 1 mod 4. And if you take a degree D bigger than 2, so start with F that irreducible, then this is stable over Q when D is odd bigger than 3, or D is a power of Q, or D has certain form. So we're not able to prove it for every D. Because actually unconditionally, so we cannot prove for every D, but we can prove for like the number of families. So D bigger than or equal to 3, or D power of 2, or power of 2 times power of 3, or power of 2 times power of 5, or power of 7, or D is congruent to 4 mod 12. So here I want to mention this result of Danielson and Swin, where they have proved that G power D plus 1 over C is stable for whenever D is congruent to 6. So D is co-prime to 6. So if D has no D has no common factor with 6, then it's stable. So basically, so after this, we were looking at these families where D and 6 is not co-prime. And also, as I mentioned, so what happens when G square plus 1 over C? So if you take C to be minus M square, then C is, as you can see, is congruent to 0 or 3 mod 4. So in that case, G square plus 1 over C, as you can see, is reducible. So what we proved was that when C is 1 mod 4, so it is not only irreducible, but it remains stable. And there's a recent result of Bimab, Hinz, Jones, Mispron, and Stone, where in fact they gave number of values of C, but when C is no 3 or 0, 3 mod 4, where so this is iterate of G square plus 1 over C is irreducible. So there are a lot of we will solve a lot of Diophantine questions and look at these points on the projective so projective points on certain varieties. So I won't go into it. Yeah. Okay. So now so this is the sort of conjecture actually one expects, in the sense that if you take MZ to be G power D plus 1 over C, and D is at least 3, if it is irreducible, then it should be stable. So this is the conjecture from the earlier results from many authors made. So we wanted, so far what we know is that we like unconditionally we can prove it for like when these co-prime to 6, or when these are power of 2, or these 3 and other families, but it's not completely known. So we have to use the ABC conjecture, and so that this conjecture is true. So I don't need to actually mention ABC conjecture again. All of you have seen it 2 times. So basically, given epsilon positive, you have a constant kappa which depends only on epsilon, such that whenever A plus B is C is less than some constant times the radical for 1 over epsilon. So I'm going to use an explicit version of ABC conjecture due to Becker, who is actually such one has also defined before. So this is the this is typo here. Becker 1994. Not 194. So this is the explicit version of ABC conjecture due to vector. So we start with ABC pairwise co-prime satisfying A plus B equals to C. Then C is less than 6.5 times the radical times log of radical to the power omega by omega factorial, or radical is of course the product of dividing ABC. Omega is the number of distinct prime divisors of ABC. Because this is also open, of course. So the thing is that so this is not really in the form of the original ABC conjecture. So we made it in the form of original ABC conjecture. This was my joint work with James Sorry in 2012. Where we actually like that explicit ABC conjecture is same as showing that A plus B C is less than implies C is less than n to the power 1 over 1 plus 3 by 4. And not only that, when if you take any epsilon less than 3 by 4, you can find a constant n epsilon which depends only on epsilon, such that whenever the radical is bigger than n epsilon, you have C less than n to the power 1 plus epsilon. In particular, for epsilon 7 by 12, which I will use in the so n epsilon is x power 204.75. So basically, if the radical exceeds this number x power 204.75, then you have this result with 1 plus epsilon with epsilon 7 by 12. So what explicit ABC conjecture implies this conjecture tree. So there is, if you assume explicit ABC conjecture, then the polynomial C power D plus 1 over C with C non-zero and D at least 3 is stable over Q whenever this polynomial is irreducible over Q. So this is about the so what we can also for D equal to 3. So we can say something more if it's not irreducible. So when okay, so when fz, which is g power d plus 1 over c is reducible, yeah, nothing was known, but when d is actually 3, we can say like how many, like we can say something over the even like well, so it's not going to be stable, but I mean, so there is going to be eventually stable. So in this regard, we prove this following theorem. So let Fg is G cube plus 1 over C. If Fg is reducible over Q, then it has exactly 2 irreducible factors for every n, and for C with absolute value of C less than 10.12. So actually, it requires a little bit of computation, so we could go further than 10.12. So, but we're able to prove that when C is up to 10.12, then it's eventually stable. But and not only that, it has exactly 2 irreducible factors. So we believe the following conjecture. So we expect that, I mean, so if Fz is reducible, then it should have exactly 2 irreducible factors, but because we can't prove it for all C. So now in the remaining parts, I'm going to give you some key ideas of the proof and maybe prove some of the. So one of the key lemma which we use is this following results. So yeah, so basically you start with a monic irreducible polynomial over a number field K, and you look at this particular polynomial C power D plus 1 over C. Then if you take G of F and G, so we can see it like if you know something about this, G of Fm is irreducible, and then what can you say about G of Fm? So this is irreducible if the previous iterate is irreducible, and not only that, G of Fm0 is not a P power in K or every P prime P dividing T. So this is a key lemma which connects this problem also with the the generalized Fermat equation and so hence in particular for m bigger than or equal to 1, so G of Fmg is irreducible if G of Fg0 is not a P power in K for is prime P dividing G, and for where J lies between 1 and n. So this is one of the key lemmas which we did for this group. So another important like ingredient which we need which we require is this capitalist lemma, which is also quite nice or interesting in the sense that if you start with two polynomial fx and gx, where one of them is gx is irreducible, then you want to say whether g of fx is irreducible. So it says it's irreducible over k if and only for every root of gx. If you take fx minus beta, it is irreducible over j beta, then g of fx is irreducible. So when we look at the interest, so we have to use this capitalist lemma. So I just want to show you this key lemma. So this is the key lemma what we actually which we use for this to prove our results. So I just want to give a short view of this very key lemma. So I start with the assumption that g of f of m minus 1 g is irreducible. Then yeah, so by capitalist lemma, if you use capitalist lemma, then g of fm is reducible if and only for every root beta of g of fm minus 1. This fg minus beta g for d plus 1 over c minus beta is irreducible over k beta. So if you can prove that, then g of fmg is going to be irreducible. Now let's look at fg minus beta. So it's irreducible if for every prime p dividing d. If you look at this number beta minus 1 over c is not a p power in k beta, because the fg minus beta is a very nice form. So if p divides d, then you can write it as c d by p to the power p. So if beta minus 1 over c is not a p power in k beta, and if 4 divides d, then beta minus 1 over c should not be of the form minus 4 times the power of beta 4 power. And so now we can ask, so what is this condition imply? So this condition is satisfied if the norm of beta minus 1 over c is not a positive power. So now let's try to compute the norm of beta minus 1 over c. So so this is same as if you take the product of alpha minus 1 over c over alpha runs over the roots of g cubed for fm minus g times the g of fm minus 1 g, and which you can actually equate it to minus 1 to the power t, where g is the degree times f of m minus 1 over c. And if you see this is nothing but the m at square of 0. Because, so minus 1 to the power t, g of fm 0. Actually, there's a typo here. There should be no brackets then. One differential, but it's the m it's right. So we have to show that this is not a peak power. So if okay, so if it's not a peak power, then this number, the whole thing is not going to be peak power. So let's get 4 divides d. Then so g of fm0 is not a square, and 4 divides t. So yeah, so the norm from this norm, what we see is the 1 minus c minus 1 over c minus beta is not a square, and so once it's not a square, it's not the norm of the form 4 times something to the power 4. So the whole conclusion is that g of gfm of 0 is not a peak power for every prime dividing p, and g of fm minus 1 that is irreducible, then g of fmg is irreducible. So this proves the first assertion, and the second assertion maybe I'll go back to the lemma. So this is the lemma here. So g of fm minus 1 is irreducible, and g of fm0 is not a peak power. And so you can do by iteration. What you can do is that if g of fz0 is not a peak power for every p dividing d and for j between 1 to m, and then in that case g of fmg is irreducible. It follows by induction. Well, so that was the dilemma. So now we have to apply it to our polynomial xg, which is g power t plus 1 over c, and k equals q. So let's assume that g power t plus 1 over c is divisible over q. So now you get this nth iteration of f0, so fn0, and let n denote the numerator. So remember that this is a polynomial with rational coefficient. So every fn can be written as some, it has a numerator, denominator. So numerator we call it n. So a1 you can easily see to be 1, and for n bigger than 1, n satisfies this recurrent this relation. So n is n to the power n minus 1 to the power d plus c to the power d for n minus 1 minus 1. And fn of 0 is n by c to the power d power n minus 1. So by induction, we can actually see that this c n minus 1 is our co-prime, pairwise co-prime. And our aim is to know that this n, this is in fact, f naught is the not a p power. So basically, we want to see that n is not a power. So for p dividing p, fn0 is not a p power unless n is a p power. So if you saw that n is not a power of p, so it's not a p power of a number, then fn0 is not going to be p power. So when n is 2, life is slow, it's trivial. I'm going to take n bigger than 2. So here, for that we require this generalized Fermat equation. So we start with because all of you know the Fermat equation. So x power p plus y power p equals g power p. So generalized, here you consider the powers. The powers could be different. So PQ are integers at least 2, and we are considering x power p plus y power q equals g power r. So a solution, there is a power p plus b power q equal to c power r is called primitive if ABC is non-zero and ABC are pairwise co-prime. So a well-known open conjecture due to Lightman and Xavier, also known as Bill's conjecture, is that there are no primitive solutions to this differential equation. So when this of PQR are bigger than 3. So because of the time, I think I is not visible here, but yeah, all of them are bigger than 3. Then this is no primitive solutions. So of course this is open, but we have some partial results. So when PQR is in a, like set which is like either P is 2 or focus P is 2, Q is 3, R is 7, or P is 2, Q is 3, R is 10, or in this given set like x square plus y power n is g power 4, or like x power n plus y power n is g cube. So and not only that, a few more like n bigger than 3, PQR is 3 and 6. So in this kind of families, we know that that conjecture is, the equation has no primitive solution. So we're going to use it. So actually, by using this, we get our main theorem 1, where we have this families of D. So we use it with some other arguments to show that when D is a power of 2, or this power of power of 3, or few other families, so we can actually prove that there are no solutions. And for the result that, okay, so to resolve the conjecture with explicit ABC, so we have some results on this Fermat equation with the explicit ABC. So what we have is that with the explicit ABC, you have no primitive solutions, except possibly for when PQR is of the form 3, 5, L, where L is a prime between 7 to 23, or P is 3, Q is 4, or R is L, or permutations of those. So except for those, explicit ABC tells you that there are no primitive solutions. So we also use it, but we still need to actually use something more to prove the conjecture completely. So maybe, yeah, first I will talk about D equal to 3, then I'm going to tell you about how the explicit ABC is used there. Let's look at this G cube plus 1 over C. So what is that when it's reducible or every divisor factor, there are actually two divisor factors when C is at most, mod of C is at most 10 power 12. So how do we do it? So we start with MC is G cube plus 1 over C, and this is easy to see that this is reducible if and only if C is the cube for some M. And in that case, it has a factorization G plus 1 over M times G square minus GM plus 1 over M square, which equal to G1, G2. So G1 is G plus 1 over M, and G2 is G square minus GM plus 1 over M square. So now, first thing what you can see is that so G1 of F, so you're taking the G1 of F, which is G cube plus M square plus 1 by M cube. So this is going to be reducible if and only if M square plus 1 is a cube, which is not possible. So yeah, it's a weaker form Catalan, or we can say the many ways to show that it's not a cube. So here we have a key lemma to say something about so to show that the threads are irreducible. So so there are two irreducible factors. So we use this notion of rigid derivative sequence. So we have G1 is G plus 1 over M, G2 is G square minus GM plus 1 over M square. Then this at 0, so if you put G equal to 0 and look at this GI of Fn 0, this is a rigid derivative sequence. So what's a rigid derivative sequence? A sequence is called a rigid derivative sequence if for every non-Archimedean absolute value this following conditions hold. So if n is less than 1, then if you if you look at this any multiple of n, for any multiple of n, the absolute value of n is same as absolute value of Akn. And if n is absolute value of n is less than 1, and absolute value of j is also less than 1, then absolute value of the A of GCD of n and j is also less than 1. So if these conditions are all for a sequence AIs, then we call that sequence a rigid derivative sequence. So as a consequence, what we can say is that so if n is less than 1 and ak is less than 1 for some Archimedean absolute value, then actually n is actually there's a thing here. So when we're going to look at the periodic non-Archimedean absolute value, then yes, is going to remain the same. So we also require some other assertions to show that there are two irreducible factors. So another assertion is that we start with a monic irreducible polynomial G over K, and you look at the cubic, and if none of this okay, so this lemma is crucial for our computation. So if none of this G of Fn0 is a cube, then G of Fn is irreducible for n. So for is n. And another lemma which we need. So basically what it says is that if you can say something about the cubic or cubic or not part of this G of Fn, then this G of Fn is going to be irreducible or not, we can actually say that. And another key lemma what we is that Fz is 3 power d plus 1 over c. Then for any prime p dividing d, if Fn is not a p power, then it's also not I mean, so this is a sort of a very easy lemma. So basically Fn0 is not a p power. If you for c bigger than 0, then you can say the same thing about it's not a p power for c less than 0. So basically it just depends on absolute value. Additionally, these three, then so the same assertion holds for G of Fn0 for any divisor Z of Fz. So basically, this lemma tells you that if you are like so our result, what we prove that when G cube plus 1 over C is reducible, it has two irreducible factors. So, but we could only verify to C to the power C less than 10 power 12. So for that we use this kind of thing that we need to only check for the positive C and also for some special C. So, but even then, a lot of computation, a bit of computations and sort of covering like when to find certain primes where for every prime you want to have a residue class where you can have a non-cubic and you can keep going. So because of that we couldn't go further than 10 power 12. So though our method it says that I mean if the more computations are here, but we can improve more, but we thought 10 power 12 was 0% useful. So now in the last few minutes, so I'm going to sort of say something about the proof of this math theorem. So this is a math theorem which I have shown you before. So basically, like when d is bigger than 2, so g power d plus 1 over c if this irreducible, then there is stable if d is of this certain form. So d is 3 or bigger than when d is 4 or bigger than or equal to 3, or in fact for d equal to 3 we use one of the lemmas I stated before, or when d is a power of 2 or power of 2 times 3 or power of 2 times power of 5 or power of 7 with certain conditions. Here one more condition, d is converted to 1 more 3 is coming in, or when d is 4 or 12. So that's general. So that recurrence for an you write in terms of n plus some power. So that we use along with the generalized Fermat equation. So non-primitive solutions of no primitive solutions of generalized Fermat we use to prove this result. So when d equal to 2, actually we use like discrete values and ideas, and for d bigger than or equal to 3. Yeah, so we try to form equations of the form x power p plus y power q equal to g power r, and what to use, I mean, we have to consider different values of d. So when or d not divisible by 3, life is I mean sort of simple because you can get an equation of signature x cube plus y 352, that is x cube plus y cube plus c square, and or x power p plus y power p equal to x square. So basically from this we try to get an equation of generalized Fermat type. So when t is not divisible by 3, actually it's simple. And so when the 2 power r divides 3, so we can get more signatures. So basically, main thing is how to bring into that form and use those results. But then there are many cases, quite a bit of some cases which is not completely covered by the known results on the generalized of the Wills conjecture. There will be explicit ABC. So I want to tell you that after all those things, actually we're left with only very few values. So with results on Wills conjecture, assuming explicit ABC conjecture, we actually need to only consider finally equation of form g square plus a to the power n a power d a of n minus 1 power d plus c times d power n minus 1 for general d. So I apply the explicit ABC with a is a power n like this a n minus 1 power d, b is c c to power d n minus 1 c equal to g square, and with the fact that this maximum bigger than radical to the power 1 plus g by 4. So yeah, so what we get is that g square to the power 4 by 7 is less than g to the power 1 plus 2 by d plus 2 by d to the power n minus 1. So first thing is easy. So basically, if so if n is bigger than or equal to 3, then you get g square is less than 1 over d plus 1 over d square minus 1. And so using d is 14 and d square minus 1 bigger than d, we first obtain d less than 21. So basically when d is big, it is straight away gives 21. So it's a little bit of some work is there, but very easy. So first we obtain D is less than 21. After that, we need to consider very few. So D equal to 14. So after ruling out other cases, we need to actually consider D equal to 14, where we have an equational form. X square is an minus 1 to the power 14 plus c to the power 14 power n minus 1 minus 1. So generalized Fermat equation of signature 237 implies n is even and n bigger than 4. So I can assume that n is even and n is at least 4. And by using Catalan's equation, we can also assume that c is at least 2. So, but then the explicit ABC in like C less than n to the power 1 plus 3 by 4 doesn't work here. So we have to do something more. So we use some other arguments and use that the radical is quite big and use epsilon equal to 7 by 12 to get it conserved. So here some bit of work is involved, but not too, I mean, so basically generalized Fermat mostly it works, but few cases where it doesn't work, we use explicit ABC. So with that, we prove this. I think that's what I can.
Thank you. All right, any quick questions?
Yeah.
Could you show the slide where you mentioned the conjectural bill? That's because usually there is the assumption that one of the p plus one of p plus one over r is less than 1. Yes.
Yeah.
Don't you? I don't see this assumption.
No, actually, the thing is that we are